Samad from Honeywell Automation. Tariq had a very distinguished career. He's currently a corporate fellow with Honeywell Automation and Control Solutions. He has been with them for almost 7 years. He was the president of the IEEE Control Society, and he's the president-elect for the American Automotive Control Council. He has been a fellow of the IEEE, he's a distinguished member, award from IEEE Control Society, and he has in 2008 IEEE Control Society Control System Technology Award. He was chair of several prestigious conferences we have in the controls community, and currently he serves on the editorial board of IEEE Press. He's very much involved in the Smart Green Interoperability Panel, where he chairs the board executive committee. So today he will talk to us about systems engineering, innovation, and control, and industry perspective and application for automotive powertrains. Tariq.
Thank you. Very good to be here. Thank you, John, for the invitation. The whole topic of systems engineering is one that's waxed and waned in Honeywell over the course of the time I've been there. And it's sort of in a waxing process again, but it means so many different things to so many different groups, and especially in a company like ours, which is very compartmentalized now. It's not like there's any kind of a unified view. So it's just good to come and talk to some of the world's experts in the area here and figure out, how we could be doing things better. So I will presume to tell you the best way to do systems engineering, but I want to give you a bit of a perspective coming from a corporate origin and a particular aspect of our work actually, and related to automotive powertrains. But I also want to give you sort of a general view of what we think about and what I would say many industrial organizations think about in terms of trying to figure out how to develop good products, how to develop them effectively, and the whole sort of the value chain involved in that, and many related issues, which all are part of being a successful company when it comes to having innovative and new products. I should say I have a little bit of a cold, so if I sniffle too much, I hope you'll be able to edit that off the video, but we'll see how that goes. So let me first give you a bit of a background on Honeywell, since some of you probably know Honeywell, but Honeywell's changed a lot just in the course of the time I've been there, in the last few years. And then sort of an overview of control in the industrial context and what sorts of things that we think about there. And then the next three sort of parts of this talk are all focused on the automotive powertrain area, which is something that historically we have not done anything in, and in the last several years we've developed some new technology that we actually are quite proud of and that we have quite a bit of success with it. So it's sort of it's almost a story in the sense about how we did that. So to begin with Honeywell. Honeywell is a pretty large company, about $38 billion in revenues as of a year or two ago. More than 130,000 employees. The company has 4 major business groups. And the largest of these is the one on the left, Automation and Control Solutions, and that's the one I'm with. The next largest is Aerospace, and then Performance Materials and Technologies and Transportation Systems. What I'll be talking about in terms of the sort of the specific project-oriented content sort of covers the first and the last on all these, so Automation and Control Solutions and Transportation Systems. So in Automation and Control Solutions, as you can see, this is the part of the business that does thermostats. It also does building automation and building management systems, industrial control systems, sensor systems, security systems. We're also now the largest provider of safety equipment, so like things like linesman's gloves and firefighter coats, which is more materials than anything else. Although even there we're now looking at putting wireless sensors in these sorts of things and having other kinds of smart systems. The aerospace side also has a fair amount of control. Of course, historically Honeywell has been a very strong sort of player in the flight controls area, and we still do a lot of flight controls. And we also are a large manufacturer of aircraft engines, not the large-scale commercial airliners, but for business jets and helicopters, and various other avionics and other flight management systems. Performance Materials and Technologies is really catalysts, chemistry, fluorine chemistry, It's a leader in its industries. This is the part of the business that invests the most in R&D from a proportion. So proportionately speaking, the largest number of PhDs in research staff, and that's because their research horizon is usually 10 to 20 years out. So they're developing new molecules, and before they can expect to get revenue from them, more than a decade will go by. So they have to have the appropriate sort of horizon in mind too, which is not the same as the businesses. And then the last one, transportation systems, and that's primarily turbochargers, and we're the largest supplier of turbochargers for cars and trucks, and we just feel great about that. So there's Honeywell is well known for controls, and this slide was put together for another purpose, and I'm not going to go through all the history of what we've done in control, but it's a pretty storied history, and we still do a lot of innovation in controls. There was in fact a time when, maybe a little over a decade ago, we adopted a corporate motto: Honeywell helping you control your world. It didn't last very long, but apparently it didn't go over too well in China. That they didn't translate into Mandarin too well. They felt that we were trying to control their world. But to give you a little bit more sort of taste of why control, we of course, a lot of you are controls people, and we all appreciate all that control can do, but I think sometimes this was actually eye-opening for us as well, for me as well in particular. We sometimes don't recognize what control has really done. So we were out in the real world, from an industrial impact, company profitability, societal impact, point of view. So it was kind of interesting to put this chart together. It's a longer chart, it's a subset of it. So these are some industries we do control in, some specific applications involved there, and what are the benefits from. So for example, oil refining, petrochemicals, oil and gas, that whole process industry sector, we are a fairly large player there. So we do things like controls and optimization for oil refineries, for clean plants, for various other sorts of process industries. A lot of it focused on hydrocarbons and petrochemicals. Benefits just with advanced control that we cite here are 2 to 15% higher production. In an oil refinery, we report $1 a barrel improved revenues from advanced controls, which is quite substantial. Significantly reduce energy consumption. Pulp and paper machines, so we do cross and machine directional control of paper machines. These are the poster child of advanced control in some respects. If you don't know what a paper machine is, it's like this huge behemoth. Yes, you're from Sweden, you would of course know what what's coming in as input to the paper machine is slurry, which is I think 99.5% water and 0.5% fire, speaking. And it comes onto this conveyor belt. It's a web, and this web can be 30 feet across, 10 meters across, maybe as much as that. And it's traveling at about 100 kilometers an hour, and the total length that this slurry travels is maybe 200 meters, 300 meters. And so going at that pace, across this width, for that long, and at the end of it, the paper is dried, of course, the different actuators and sensors, and we measure the accuracy, the thinness of the paper to within microns. We control it across the sheet to within microns. And that's done with all the very sophisticated sensing and control equipment, as you can imagine. And the other benefit that in many of these applications isn't just sort of performance in the sense of variability reduction. It's also things like calibration time. So with the right model-based tools, in many cases, that's as much or even more of a benefit than the performance aspect. How much faster can you turn the product around? How much faster can you do the control? Now, building control systems, 7 to 1/3 reduction in 7%, 1/3 reduction in energy costs. We're actually doing some work in adaptive control of heating, ventilation, air conditioning systems in buildings, and we're doing it remotely, so remote adaptive control of buildings. Then on the aerospace side, commercial aircraft engines, space vehicles, of course, a lot of control technology here as well, and military and unmanned aircraft as well. So very diverse and substantial impact from advanced controls. So that's kind of the message here. Okay, so let me give you a little bit broader sense of control in industry. And perhaps the primary message is that every industry is different, that there is no one thing as sort of cookie cutter control technology. You have to really understand every industry sector and every application, even in the industry subsector. So things that, and in an academic context, and certainly until I would say 5 to 10 years ago, I really never thought about most of these issues or was politically aware of them either. So even things like the value chain. If you think about how does a controller end up in let's say, an aircraft, what's the process that goes? Somebody comes up with an algorithm. How does it actually end up in the aircraft? It's not like the algorithm developer could be a researcher, isn't going to go to the aircraft manufacturer and install it there, right? That's not how it happens. So you have to have an appreciation for how that happens. There's a significant difference in across industry sectors where control is used in how many identical copies of a controller end up in the field. So the contrast there would be, on the one hand, say something like an oil refinery, where for every refining application, a separate controller is developed, a separate model is developed, it's identified, and the controller using, of course, similar algorithms, similar templates, but basically it's a new controller customized for that case. And then furthermore, it's comes to the next question as well. It's tweaked online as well in the course of initial operation and commissioning, and so you have the freedom to do that and get the controllers. And so that's on one extreme. On the other extreme would be the automotive case, right? So you have a controller for let's say anti-lock brakes, for example, the chassis side, or the engine, the powertrain side, could be for fuel injection control or whatever application it is. But once you've developed the controller and you've satisfied it that it's working well, now you're going to put it into perhaps a million or more cars, and it's going to be out in the field. And there is no prospect short of doing a recall for being able to do adjustments. So very different in those two cases, and as you can imagine, the degree of assurance you as the designer or the company that's manufacturing this end product has substantially different how much assurance you need to have that this is functioning as perfectly pretty much. Right? In one case you get 4 to do some tweaks, in other cases simply cannot. What variety of conditions, of course, will be encountered in practice, how nominal versus off-nominal sorts of conditions will be seen. Is the application safety critical or not? And often when it's safety critical, there are regulatory and certification requirements, and those impose significant constraints on applying control. And lifetime of the application, as you might imagine, something that's developed or something that's we do, like a cell phone. Apparently, in the course of putting the report together for the Control System Society on the impact of control technology, we were talking about where are the most control loops used. And initially, I was saying, well, it's probably automotive, and I was having this discussion on Carl Oster, in fact, and Carl first said there are probably millions or there are probably millions of theories in the world. I'm sure there are many more than that. There are probably hundreds of millions. Let's think of all the cars. And then Robert Hudson from Carl actually talked to him and said, well, every cell phone has at least 4 closed loop controllers. So that's by far the largest sort of deployment of control loops out in industry. How many instruments are there? Okay, cell phones?
There's a lot. Thermostat. There are billions, not hundreds of billions.
How many there are in the average house?
Well, yeah. So no, but I'm talking about a particular device or something. So it's like what's the one product class that represents the largest number of
Toilets.
Yeah. Okay. Yes. Okay. Digital, sorry, actually, more specific. Advanced control or something.
But there are many other controls.
And actually, I was also trying to limit it to engineered controls because on the biology side, of course, I mean, that would certainly be. Okay, anyway, so advanced control isn't really just about the algorithm. In many cases, the algorithm.
So why is it still invisible? Because we have done such a good job that we don't realize it.
Yeah, I think we are not very good at promoting ourselves. That's for sure. So you have to know the technical aspects are certainly important, but the industry is important. The work process and environment, who's going to be actually operating these control systems that you develop, that's important. What are the benefits that you'll get from it, and those vary, of course, from industry to industry. And so understanding this picture is quite different.
Actually, said this stuff is really in collaboration with Craig Stewart, a colleague of mine who is in Vancouver. We have a paper in transactions and process.
So let me just say a few more words about each of these
Topics, or most of them. Technical considerations, right? These are the sorts of things that vary from application to application. The plant, how nonlinear is it? How multivariable is it? How important are constraints to handle? You know, the major reason why the process industries advanced control has been, and some of you may disagree with me, but that's the most successful application of advanced control, most industry which has been the most successful application of advanced control is the process sector, and significant degree is because of the constraint handling that some advanced control methodologies, and some of the multivariable context. But other things, of course, are important too. Sensors and actuators, obviously, their quantity, their quality. What's the platform, the computing and communications? How much horsepower do you have? There's some examples of that later. The software structure processes. How is the software developed in those industries? Certification sometimes comes into play here as well. Is the legacy code that needs to be incorporated when you start with the sheet of paper? How is control tuning done? In some cases, there are very objective criteria for tuning controllers. In other cases, sort of left to the operator to figure out how to do it. And then tooling is getting to be, I think, the really critical piece. We need more and better tools to just get control out to a broader.
Where in this chain of controls development activities would you see the most potential for improvement? Or what do you think is the area where the most mishaps happen in the control development?
Well, I think some of these are constraints more than anything else. Certainly, the platform is a constraint, and in many cases that's going away. Just to give you one example, thermostats. You can still buy thermostats that have 8-bit microprocessors in them. But today's the modern thermostats have 32-bit or more, or better processors. But a lot of that horsepower is actually used for the display, not so much for the control communication. So you could say, well, there's a lot of space for improvement in what you could do from the point of view of the complexity of the control algorithm in the thermostat. But the question is, who needs it, right? I mean, if you could control the temperature in a room to within 0.1 degrees versus 1 degree, would it really benefit anybody? Would anybody pay for it, right? Yeah.
Oh, it's worse than that. The thermostat is point control, right? So
yeah, so in fact,
the room is.
Yeah, so you would have to do that in combination with more sensors and more actuators. Yeah, you'd have to have more dampers individually controlled in a building and more sensors. Yeah.
But I think in the first step,
Requirements and modeling.
going from requirement modeling, that's where the most improvement is done. Because right now,
I think I agree.
Yeah, I don't know.
Yes.
I think in some industries, so the tooling hasn't caught on, and that's what limits applicability. So you have industries where there's a need for advanced control, yet for whatever reason, they don't have PhD level control people who know how to do all this advanced control in mathematics that we do.
but maybe in the first two, since we got agreed, you should spread the reservation in first 3 months, so I have the overemphasis on requirement.
Oh, yeah, I think there's I will come to that. How long is this? Till noon?
There's also a big issue with maintenance, right? Because, it often happens that a sophisticated controller would be much better, but there doesn't exist the capability to maintain it.
Yeah, well, maybe generally speaking, but yeah, you're right, Bill, and in fact, I said it.
Well, so if you want to be that way, you put controller deployment and maintenance under requirements, and then for sure, requirements are the biggest.
Well, that's what's called lifetime, life cycle.
Yeah, no, that's right, so they could be there.
But to give you a bit of color on this remark I made that the process is the most successful sector for advanced control. But in fact, in many cases, one hears about these advanced model-predictive controllers that are implemented, installed, do really well for 6 months, then something changes, and then they're not doing so well, and then they get turned off, and they stay turned off. So yeah, exactly, that's a big issue. And to me, that's also something where, in a sense, tools come to play there as well. If you had good tools that operators could use to keep things adjusted to something or whatever. I mentioned this issue about value chains, and so here's a picture on the left hand. I don't know if you can see it all the way in the back. Trying to read it out. Aerospace on the left side, process industry on the right side. In each case, you start with, let's say, an algorithm. So you as a researcher, could be in industry, could be in academia, comes up with an algorithm that you're convinced based on your simulations is like the greatest thing for flight controls. It's slice spread, not that big, it's slice spread, flight, and so now, how does that progress, right? So you would, it's not like you can go, as I said, and talk directly to the aircraft manufacturer and implement that controller. In fact, the controls for the aircraft manufacturer usually come from a controls company. It depends on the aircraft manufacturer a lot, so there's significant variation within the industries there as well. For example, Boeing does a lot, and the majority of its own flight control. Other companies like Schneider and Embraer probably do not. So companies like those would rely on some controls company to supply the controls. And in many cases, even that controls company isn't necessarily the one that's doing the control algorithm and translation to software. There may be some third-party application out there. And of course, that's not necessarily the ultimate customer either. The ultimate customer is the end user, which could be the airline or the leasing company, right? And so one reason to keep this notion of value chain in mind. I'm not going to the process industry one, but you can see there's similarities and differences there. One reason to keep this in mind is that as something goes through a process, you have to have benefits in mind at all levels. Right? If something's going to be really good from the point of view of the airline or leasing company, that's not good enough. There has to be something in it for every organization down the value chain. And of course, there is some flowing back of benefits to the end user, but that is often not enough. So it's often, in the process industries, for example, you could say, well, if you were to install, if you process plant owner were to install my sophisticated controller, you could get this benefit from it. Right? Well, what does that mean for the EPC, the company that's actually going to be installing the whole automation infrastructure and system? Does it really matter that much to them? What benefit do they give? If they have to put more expense into instrumenting the whole system, they may say, well, it's really a wash. I'm not sure this would be that beneficial to the customer, even to me, and so on. So that was sort of the value chain, and this is a sort of a simplified diagram of how control ends up being developed and deployed from a functional point of view. What are the functional aspects involved? And again, two areas here. This is automotive engine control, and this is paper making control. And I won't go through these in any kind of detail, but one thing I want to point out, well, first of all, just generally speaking, so here you start with the engine and the desired performance. That's what you start with, or that's sort of what you're given when you're doing powertrain control. And then through various sort of calibration, development, testing, integration, loops back and forth, you end up with something that can be certified and released. On this side, you start with the control functional development. You have general requirements on control for that class of systems, in this case paper making machines that you develop this for. And you end up again through some sort of sequence of processes and iteration to something that's deployed, and then it can be maintained after commissioning. But one key difference here is that where the plant enters into the picture. So in this engine, the powertrain case, the plant enters right up front. When you do a powertrain control design, you are generally starting with some idea of this is the engine, and there may be some variation that's possible based on the results of explorations with control systems. But in general, that's sort of the idea. This is the engine I'm starting with. In the paper machine control case, you're not starting with the idea of this is the paper machine I'm starting with. You're coming up with a general template, let's call it, for a paper making machine control system. And it's something that, when deployed, can then be configured and customized for a particular paper machine that this is going to be installed for. And so that's the plan that goes in there. Another issue, again, going back to benefits, the issue of benefits. What are the benefits that come from control? And of course, when we write our papers, at least when I wrote my papers, I was harping always on things like, setting time or
energy or sort of actuator movement or something like that. But there's much more to it than that, and often those are not the key things that are driving adoption of advanced control. So a big deal in my mind in many industries, and of course it's all very industry specific, is accelerated development time. And especially with model-based design techniques, I think the large major reason to adopt them is because you can really expedite the whole design development process. Control can give you enhanced insight, or in fact can help you simplify your development process in many cases. System performance, both in normal and off-normal sorts of conditions. Reliability and fault tolerance. In some cases, even reduce cost of hardware. In some cases, you may not need an expensive sensor if you have the right sort of estimator, for example. And this is all in the context of what's available today, what are the alternatives, and what's the business center. I threw this in there because I was talking about PIDs with somebody. Why is it that PIDs are so popular, right? I mean, certainly it's not purely from a performance point of view, but there are some things that I think are important to keep in mind that make it so much easier to apply. Modeling is not required. I think probably we are all convinced in this room, I hope, that modeling is a good thing. But yet there are challenges to modeling, and I think it's one major reason why PIDs continue to be used. People who don't know what a model is can still do something with it and still put something with it. And similarly, PhDs are not required. They are familiar to the people who do the installation and commissioning, and the people who actually operate those controllers in many places as well. Processes are well known and established, and of course, say there's some simplicity. All that being said, I think there's actually no shortage of success stories of advanced control, and there may be all these. But we have, in all these, and any one of these success stories, if you look probe at them, you'll see that there are good reasons why these advantages have been overcome. And it's not that even in some cases, PhDs may be required, modeling may be required, but the benefits are such that they outweigh whatever advantage you would gain in terms of cost reduction or whatever from these aspects of the Okay, so let's move on now to talk about a little bit about automotive powertrains. Actually, there's one more slide I think is listed on there. This is one thing I was thinking about on my flight over, so I put this in. Large scale versus embedded systems engineering. And I think there is actually quite a significant divide between the two in the practices that are employed. And much academic research, certainly not all, and certainly in fact, we talked to John this morning, a lot of people who work in the embedded systems topic. But at least traditionally, and John maybe goes to the IEEE Systems Council or something like that too. There's been a focus on these large-scale programs with hundreds of thousands of engineers, long time horizon development, a lot of issues with getting things into the development time and cost, and that's what's driven a lot of research in systems engineering. On the other hand, many control applications in the commercial and industrial space are really for like devices of one sort or products of one sort, not large-scale complex things. And to me, there is a significant difference there. In particular, in these cases, so we part of Honeywell I'm associated with, we put out I don't know how many hundreds of thousands of products a year. These are all developed within a few years horizon. I think very little goes more than 5 years, I would say. And the key issue is getting them out rapidly. We're always in product development mode, getting more products out very rapidly, making sure they're reliable, but at the same time being agile and iterative and responsive to customer needs, but perhaps not necessarily overly responsive to customer needs because customers change their mind as well. So,
Tariq, understand that our customer wants the first book, because we get paid to do research mostly by the government, and the industry doesn't normally provide a lot of support for actual research.
True.
But they hire our students.
Yeah, but
support. They do what we call the system engineering, take our cost of ownership, the students much more shorter than the results.
yes, but I'm.
To understand who won.
But if I'm deciding what to do, my first priority is thinking of my family and my students.
Yes, I can understand from your point of view. From the
It's changing rapidly.
I agree that it would be better if it was different.
Anyway.
So anyway, I'm giving you my point
And
of view.
primarily it's driven because most of the companies have closed down their R&D labs. That's what's driving.
Okay, let's move on to automotive. So transportation industry. Software is getting more and more important. Control is getting more and more important in this sector. More than $1 billion spent on control design and calibration a couple of years ago. Lines of control code increasing by a factor of 10 every 8 years. The projection is development cost for software will exceed hardware before 2020, sooner. And there's really some lack of systematic approach, at least. So probably discussions we have. And what's necessitating, what's driving advanced controls? One major driver has been emissions reduction. And the emissions allowances, the emission constraints, both for nitrous oxides and particulate matters in Europe and the US have steadily been ramping down. So from this level in Euro 1 regulation down to somewhere over here in the Euro 5.1. In the US, this level, and this is like something like 0.333 grams per kilowatt hour of NOx, of particulate matter, and about 6.6 grams per kilowatt hour of NOx. So that was the US regulations in '91, and now we are at this little dot that you can barely see in 2010. So steadily ramping down, and what's been happening is control has been recognized as really essential to achieving these restrictions. Of course, it's not just control, sensors and actuators have been going up steadily as well, so a significant increase in sensors and actuators over time.
And the processes themselves.
Huh?
And the processes themselves. I mean, one question I'm going to ask you now, is that everything you described is fine as long as we separate sense, decide, actually. Now we came to the point where the plant and the controller cannot be easily separated this way. In other words, and that was clear in the chemical engineering, right? You have to somehow redesign the process to make the control easier, vice versa.
Yeah, I mean, to some extent, yes, but I think in most cases, we still come after the fact and too late. So we need to change that, and maybe in some industries it's changing
We
more
still
than
do
others.
not have a maintain a precise theory of design of our control,
Analog control.
including implementation, not just tell me the algorithms. Just tell me how I'm going to put it physically in the plant.
It's analog control.
Another control, we have.
Where do we use analog
Do
controllers?
you remember Gilbert Brothers?
Huh?
Do you remember Elmer Gilbert Brothers? The simulations of the aircraft training machines. This was a very successful application of analog control before we all did, digital control. And now it's coming back, process control, and many of these things where you cannot separate the controller from the plant.
Are you saying you're doing control without digital computers? No?
That's right. You do the control like the physics, within the physics of the system.
Yeah, that's right. That's
But engine, right?
Hmm?
But engine doesn't have control. It's new physics, you change the physics, and that will provide the feedback control. It's coming back.
Yeah, I mean, probably beyond the horizon that we are thinking about
It's
from the
coming
point
back
of view
primarily for
of.
one reason, for smaller dimensions. When you go to smaller dimensions, this becomes much more fuzzy that you can actually separate by computing.
We talk about thermostats earlier. The old Honeywell round thermostat had an analog controller, right? It had a mercury switch in it. Yeah. But nobody, I haven't heard of anybody saying, let's go back to analog for
That's
thermostats.
that's what I call the MATLAB generation weakness. Right? Just because you can do everything in MATLAB modeling, you solve the problem, not exactly. But it's a long thread.
And the connection, so Honeywell has never really been a major player in engine control.
Yeah.
But we are now, and have been for the last 10, 12 years since Honeywell merged with Allied Signal, the largest supplier of turbocharged engines. And turbochargers, we're largest supplier, sorry, not turbocharged engines, largest supplier of turbochargers. And turbochargers are really seen as instrumental to driving reductions in emissions because they allow you to increase power in an engine with a smaller engine. So, sort of small capacity engine. So I won't go through.
But is it required change the control before you can come to control?
Right now, there is very little by way of controls in turbochargers. Right? So that's what we are trying to change. Or very little by way of advanced control. There is control. There's
But it changes the physics of the process first, and then try to apply control.
Yeah, and I'm sure the people originally people changed the physics of the process, and there was at that time no control. These were purely mechanical passive devices. Now they have movable vanes which are under control and some constraints on turbo speed and things like that. So it came later. I mean, it's an unfortunate fact, but that's still the case. That we come too late into the game. So what's a turbocharger? Just to give you a quick overview in case you don't know what it is, but so turbocharger really takes the energy, the exhaust energy coming out of the cylinders, right, which is exhaust coming out of high temperature, high pressure, a lot of energy there, and tries to use that energy to increase the efficiency and the combustion process in the cylinders. And it does that by taking the exhaust and running it through a turbine. And so it's high temperature and pressure. The turbine speeds up to something like 250,000 plus RPM. And connected to the turbine is a compressor through a shaft. And so this compressor is just taking the outside air, compressing it, and putting it into the engine. So you put much more air into the engine as a result of taking this energy out of the exhaust. And because you're putting more air into the engine, you can burn more fuel in the same size engine, and so you can have a significant increase in engine power. And there are many different variations. This is sort of the simplest stage, and then the variation of many others. This thing called the exhaust gas recirculation valve is quite crucial in many of these designs. It allows you to reduce NOx emissions in particular. Many configurations, they all have a need for control because these turbochargers have variable vanes that can be controlled now. The EGR valve can be controlled. So they're all minor, they're all nonlinear, and they're all actually complicated from the point of view of control. So how is control done today in these turbocharged engines? So here is sort of a schematic. This is generally sort of a common way of doing things. We have a boost pressure sensor and an airflow sensor, and each of these are used to control one actuator each. So the boost pressure sensor is used to control the turbine blade position, and the airflow sensor is used to control the EGR valve position. And this is a highly nonlinear process, and through some combination of PID controllers and table lookups, we can do an adequate job from the point of view of what we're trying to do today.
Actually, I know people that try to apply MPC to exactly that.
That's what I'm going to be talking about.
That's not really.
So, and a big reason for this is because of the horsepower issues, right? Computing and memory footprint. So, we do advanced control in the process industries, and that's because we can afford high-end processors. This picture is a few years old now. It's probably an order of magnitude higher, perhaps, I don't know. And in the automotive case, again, these are increasing too, but they're still quite limited compared to what you can do in process time. So that's sort of by way of background. So then we said, we are world's experts in advanced control. We have all these ideas in controlling all these applications. We think we should, and we think that this is a major trend. Emissions are going to get tighter and tighter. Fuel economy restrictions are going to be tighter and tighter. We should be able to apply our advanced control technology and gain business benefit from it in this space. And in particular, we've been among the leaders in applying more predictive control, in particular in the process industries, and I see most of you kind of have an idea what predictive control is, but there's a quick couple of that anyway. So model-predictive control uses a model of the process, and it uses the model in this look-ahead fashion to predict what might happen under different actuator, different inputs to the process. So for example, you give this input to the process, you have a model, the model tells you this is your past data, that your process will move like that, right? And you have some set point you say you might want to get to by some time, and some other constraints as well, and some other requirements as well. And so you can, in simulation effectively, try different sequences of control, trying to see which one is best. And if you, in the appropriate cases, this ends up as a closed form solution. It's not like that in a fashion. But it's still quite complex computation. Well, in the last decade or so, there's now been this development of this fast MPC technology, parametric control, fast model control. And we've been working with Francesco Borelli now at Berkeley in this area. And really what this technology, this idea does is it solves this iterative optimization problem offline completely. And then online, it captures the whole kind of computation in terms of a table lookup and an affine control law. So the idea is you in your state space, you based on how this is done under constraints as well, so the constraints involved too. You partition your state space into a number of regions, and then within each region, you pre-compute what the right control law will be, and then you just look up which region you're in online.
Are there some restrictions on what class of problems produce in control law?
So this can be the model is linearized at every one of these things. So once you do that, you get, and with the constraints, and so there's limitations on what the constraints, some of the constraints can be. So I think both ramp constraints and.
You trade off the complexity of the online calculation with having many regions in the
Yes.
offline, and that in each region gives you very simple control.
Yeah.
To us, is it clear that doing the approximation beforehand doesn't subvert the effectiveness of the controller? You can, I think, construct examples where really nonlinear controller is computable and is substantially better than any controller that you arrive at by linearizing, linearizing the problem of things.
That's right. This is linearizing, but all applications. I mean, this technology, linear control, is what's used everywhere in the processing industry. So, yeah, I think there are cases where true nonlinear MPC. In fact, we've been looking at that for some chemical processes as well. But there are cases where linear MPC just won't cut it. In fact, but for the vast majority, for a large number of cases,
Human posture control is also. Human posture control is another example where just float the baby out of the bathwater.
But Borrelli is using this primarily for field control.
Say again?
Borrelli has been developing this for
No, he's been using this for automotive, and I think probably.
I think the main limitation is really how many different affine regions you need. I mean, if the model is too complex, then you run into trouble. Is the correct? Are you using the multi-parametric toolbox from Manfred's group?
Yeah. So this is Manfred's group, and what we do, I won't talk about it in detail, but we've developed our own extensions to it primarily for this reason that it ends up with the memory footprint grows too large for any kind of complex application. So you need something in between. So we figured out where it goes out. So we said, we can do this. We now can do MPC fast online. Let's go and show the world what we can do. And so we went and talked to a few customers, and we talked about our control heritage, and they recognized that control is a big deal for them. Many of these customers didn't actually have very strong control groups at that time, and they still don't. And so we said, this doesn't need that much effort. You just give us a few years, and we can show you what we can do. And so with a bunch of customers, we did experiments like that. So this is multivariable control over the new European drive cycle. So this is used for emission testing. So, and this is just sort of the basic experiment in a way. It's a small engine. It has a single stage turbo and an EGR valve. And we said, okay, you give us any set points you want, provided they're realizable, I guess, of boost pressure and manifold airflow. And we will show you that we can control to the set points, and these are in fact two curves overlap, actual and set point. And you can see what we are doing with the various sort of parameters. Like you see what the NOx emissions will probably be like. And this is actually on a test cell, so this is on a monitoring process. Variable geometry turbine, EGR. And we did this, I can't remember exactly, but in a matter of a few days, 2 or 3 days or something like that, going from scratch to this.
And this was done on an ECU with what they use in terms
So
of
they all have these systems where they can tie into the ECU and you can bypass the ECU. So I think these were probably all.
But this was a realistic computation power and memory on ECU, right?
Yeah. All sort of that's it. So they said, okay, well, we can do this. I said, oh, wow, very impressive. Well, it doesn't stop there. We can do many other things too. So so this was, NEDC, like, this is now the FTP. This is the US cycle, US emission cycle. This is the medium-sized engine now, not a small engine. And this is two modes of the FTP cycle. And here we said, well, now let's show you what we can do with controlling to manifold air pressure, so you give us a set point on that. But now you can give us turbo speed constraints and the variable geometry turbocharger bearing position constraints.
But those are important things. You don't want the turbo to overspeed and it often does, and that's the issue. You want to keep all of that. And we said, with our technology, these can in fact be time varying. It's not like you have to give us constraints ahead of time and they're fixed forever. These can be time varying constraints, and we can show you what we can do with that. And so they gave us those. They gave us time varying UGT constraints, which we met in the system.
What is the green curve in UGT?
That's the constraint. So this was the time varying constraint on the variable geometry turbocharger speed. Speed, or it's either speed or position. But I'm not quite sure. But it's a constraint that the controller made sure. And the point was that you don't have to fix the constraint ahead of time at some level. You can change it in some points.
So you used this explicit MPC for that. How many affine regions do we end up with?
Geez, I don't know. I wasn't at the plant doing this stuff. I was leading this project at that time, but yeah, I took that. I mean, this is, it's still sort of it's not a very large scale system. There's 2 inputs and basically 2 outputs, so it's not. In fact, this is saying maybe just 1 output, but they are more constrained, so maybe there was. And then we did like a dozen of these things. I'm just showing you 3 of them. This is the last one. We said, another interesting thing we could do is, if you have a NOx sensor, we could even do, in fact, time varying NOx constraints. This is not showing the time varying. So you give us a constraint on NOx and nitrous oxides, and give us set points, and we will meet our set points as best we can, and we're just assuring that we don't exceed the NOx. And this is all done in a model-predictive control fashion. So, all these customers were extremely impressed. They said, wow, we didn't know you could do stuff like that, and what of this stuff, and this seems exciting, and that. And then we started talking more and said, well, okay, so what's the next step? When can this be a product or something? Well, we need to think about that a little bit. You have to understand how we do things here, and how this stuff really works, and what are the issues that are involved. You have to understand the people we have, and who's going to be developing all of this stuff. So it was really kind of a wake-up call in a way. Here we were just focused on very narrow performance sort of issues, which we thought were really crucial. We thought we had understood the industry trend and all of that. And then all of a sudden, so yes, this sounds really exciting, but there's more to it than
And now first about the systems engineering.
And some of these other constraints are really different between regions. I mean, we're experiencing it's very different between Europe and here.
Yeah.
And Japan, for that matter, actually.
So we've been now working with customers in all of it. So here's one thing. So you have to understand how we do it. Okay, and are you going to be able to, if we use your technology, can we continue to do it the same way or not? And if not, what does that really mean? Okay, so how they really do it, sort of, it's a big picture I showed before. There's some loops that are not shown here. First you have the engine, you do the steady state calibration of the engine, then you go into some control development, then you develop the software, then you do some calibration and tuning, then you do certification, release, post-release. And at the end of it, you have to remember that you end up with a controller that will be implemented on 1 million, perhaps, engines every year, produced for some number of years, and that will be out in the field for 20 plus years, and it has to work really, really well throughout that whole time across the whole population of engines. So, it's not like we didn't know this stuff, but anyway, I think we didn't really understand all of this. So now, if you're doing this MPC, how does that work here? Does it mean we don't need to do this anymore? Or we need something more than steady state calibration? The answer is yes, in fact. And we need more iteration involved here, and who's going to do this, and do you have tools available for it, and all of that stuff. So we ended up sort of taking a step back and going back and doing some more homework, and ended up with something that's now a product called OnRamp. And it has modeling, control design, and control deployment. It starts with physics-based models, which are sort of pick and placed from a library of components. Then there's automatic identification done, both on a component level and system-wide level. So it's system identification, kind of these dynamic models that are then good for control. I mean, the physics-based models are not optimized for control application.
it, so that we end up with this sort of linearized model testing use of control focus on. And then figuring out what does that mean in terms of putting it on the ECU and what's sort of the tools that we need to for. And really, it's helping, and the whole idea turned from being all about performance and emissions and how much better you can meet set point and all of that, to how much quicker you can turn your control designs around. So how much faster you can do iterations, trying to try different things. So, the traditional picture is sort of the hardware selection piece, there's sort of production software emissions calibration, and then there's OBD software calibration on the diagnostics. Traditionally, you could only do some couple of iterations here, especially because every time it was new hardware and you ran something on a test cell, so it was actually quite expensive to do. Now with this model-based paradigm, you can turn the crank that much faster and that much more often. And then similarly on the calibration side as well, so you reduce significantly the whole time. And of course, there's the performance aspect as well. So it used to be the case that all this stuff was done pretty much on a single input, single output basis. And now this is sort of projecting ahead a little bit, because we're also now working on some after treatment devices as well, like SCR is a NOx emission reduction technology, selective chemical conversion, and some oxygen catalysts and regeneration as well. But all of this you can put into one multi-input, multi-output module. We haven't really focused on the fuel side really, particularly on engine brake controls, but that's not a part of what we're doing.
Who verifies that the system will last for 10 years?
Yeah, so you have to go through certification for the authorities, and they have to do some sorts of extended testing. But really, the car manufacturer has to be pretty sure that this will last. So you have to convince them as well.
So yeah,
The cost of recall. I think the cost of a recall is what mostly drives this.
No, I understand all that, but basically, the question is, if I'm a car company and you tell me it's going to work for 20 years, I ask you to prove it. I'm not going to accept a bunch of papers, right? And in this, I'm listening specifically for who is going to be responsible for, what is, from the car company's point of view, an extremely important test.
Yeah, well, I mean, that's handled today, right? I mean, often these engine manufacturers not the same as the car manufacturer. Right?
Yes.
Very often. So the engine manufacturer will sell it to the car manufacturer, and it'll come with some assurance, and the car manufacturer has to know what processes have been followed by the engine manufacturer, and so they have to. That's true today, and it will continue to be true under any kind of new design.
Yeah, that doesn't, so who's going to do it? I mean, in your chain of companies that are involved in this, is it Honeywell? Is it the car company? I mean, it seems to me neither of those have.
The engine integrator, and then the experts very defined application. For instance, it's not perfect. I mean, there are records.
So it's not Honeywell in the sense that it wouldn't be, we're just providing this sort of thing that goes on the ECU. It's the whole thing that has to be verified.
Actually, this is you can verify very easily according to the NDAs, not calculations.
Yeah,
Okay.
and everything is out in the cold and at altitude and all this other stuff.
So I mean, they do driving, right? I mean, that, in fact, northern Minnesota is very well known for the testing, right? For
This guy.
So we've really tailored this right now for these sort of
Well, the question that I guess that I follow up with is, what happened with the aircraft design, the 777, 787, by forming a very structured system engineer, where they were able to reduce the cost and time for the certification? Has that happened in Auto?
So this is still happening, I would say. I mean, I
Even
don't
the
actually.
777, they were able to fly with 30% less than before because of other certifications that could do and prove that the automated process good enough in the past FAA.
And they had to try it from the 787.
787 is very long history because a lot of triumphs just don't stick on the battery. That's really not a good engine.
It has more problems than the factory.
Huh?
It has more problems than the factory.
Compare what they achieved after
So model setup, we have a library of components tailored for this application. So filters, compressors, charger, coolers, various turbines and valves. You can pick
The
any
library of
custom-
components is done in different software or in one software?
It's all in one software.
Or one software?
Okay. And so you do that, and then you run one test cell experiment or some number of test cell experiments and get the data. And initially, you do model fits at a component level for each of these models. So these all are parameterized sort of nonlinear ODE kinds of models, and you sort of put them there. And then you do a global fit as well with all of these. And now you have what you need to do the control design. And when you do control design, you can specify where you want, what actuators you have, what sensors you have, which set points you will be using, and where you will be imposing constraints.
And can you inject actual test bed data from a test engine that you may have in the lab, for example?
So this modeling process, this model fit, is all done with actual engine data.
As well, I have some engine like I've seen in Sweden, okay, where I have the engine in my lab and I run it. And I get online measurements and I run this in parallel. Can I inject some of the measurements and fix some of the problems?
Yeah, I mean, so that's
Real time, but not options.
Oh, I don't know if you do that. So this is done. You get the data, you do it offline, and you optimize your.
For both in Lund and Lund is another unit. I would say this thing. They have this actual engine in the lab and it's instrumented. Actually, you can see it through the glass which have inside. And they have it on the design of the product. In real time, you can compare and they can adjust. I don't know if the model and the product is fascinating to see, especially on the thing that is zero in the emissions and tourism. These are very difficult processes.
Yeah, so I mean, of course, you have the model here, so you have to verify that the model in closed loop with your controller is replicating what your test numbers are. So we can look at that. And then tools has been a big part of it. So sort of so with OnRamp, you can do drag and drop engine components, and the routing is and wiring is automatically generated, taking the dynamics into account. So it takes 10 to 30 minutes if you use the optimal modelers. A lot of other stuff as well. So doing this MPC design is some ways complicated. There are these parameters which are the output horizon time, the control horizon time. These things are very geeky in a sense, and we managed to replace those with slider bars that are basically the robustness, something that you expect that people in the shop will be able to
Runs in simulator?
I don't think it runs. I should know the science of it, but it looks like something.
Yeah,
It's something we've developed, and I'm sure it's available online somewhere. I'll show you there's a URL that answers that. Yeah. Except I'm not sure whether all these places will have simulink or not, so that would be the thing. So on the other hand, I don't know whether you want to about that. Yeah. So, sort of a systematic procedure, and it sort of changed how we do things. So now, we configure the model first, then we calibrate the model using the data, specify the control problem, synthesize the control problem. Of course, there's iteration and testing involved. And then the Nemo controller integrates into the production software hierarchy. So you end up with software that then can go through the regular software development process.
Does anybody or have you tested the user friendliness of this software with respect to the customer? There are complaints, right? That
Yeah,
I'm not as sophisticated as you are in my engineers. I want to use it.
This is being, I think it is on some couple of dozen plus customers have this.
So the engineers or the auto industry, they can use it for learning.
I'm sure there's some learning involved, we get training classes. And what is going back to what I talked already. So, so the MPC is really behind the scenes. There are some patent extensions as well. One of these relates to, so explicit MPC, it shrinks the number of operations, the computing costs are involved, but it makes the memory sometimes too large for ECUs. So we've come up with some variations and that allow you to make So, benefits, transient control on engine in less than 2 weeks. So clean sheet development time for transient control reduced mostly several months to a few weeks. Literally, this is the scale of the improvement in they estimate one saving of one full-time equivalent person per license that you file on this software. Significant fuel efficiency is projected here. Various other things as well. So this is it's one that I took the Control System Technology Award last year. It's out there on the web. There are quite a few papers and things like that on this too. And a lot of this stuff is not practice that have been issued, so there's no issue talking about it. So it might not be more. Okay, so just to wrap up, I just sort of highlight a couple of things that I mentioned already. So advanced control has to be seen in context. You have to sort of look at all the various issues involved in putting control out of the lab and into the product and into its algorithms. Talked about this OnRamp development, which does modeling and control, model-based control using this explicit NDC kind of idea, and includes a little bit now for cycle time in particular, more and then going back to just this bigger issue about advanced control applications and systems engineering. This is again just observations that arise. And how are the problems addressed today? It's not like we're trying to solve fundamentally new problems. In many cases, industry has been addressing those problems. They've been doing it maybe in ways that can be improved upon. And when it comes to emission controls, we do have low emission vehicles. How is the industry doing it today? You can understand that. It's not like we're coming up with something that's completely sort of unheard of before. Understanding the requirements and the reasons for them, and this goes back to sort of having that understanding that value chain in a way, but also and mentioned this earlier, talking about it, and more as we do these more iterative, more agile development processes, part of the mindset is changing to going from, well, the requirements are set after you've discussed them with the customer and agreed on them, and now you have to deliver to them. To this process of, you have some requirements from the customer, and you go off and do something, you show it to the customer. The customer doesn't often know what the requirements are themselves. It's quite common to develop something and the customer will say, well, I didn't tell you this initially, but in fact, this is also really important. This other thing that I did tell you wasn't really that important, so could you go back and do it, right? So having this iterative sort of process that's not so driven, doesn't hold the customer requirements as being sacrosanct, is really a significant sort of driver for us for bringing more agility into our product development and to our systems engineering processes. Understanding if and how advanced control can be a solution, what are the barriers to change, there will be many barriers to change, and also what are really the costs and what are the benefits, and we have to be able to make that trade-off effectively. And tools are more and more important, of course. There's requirements driven to some extent, I guess, model-based control design. And then just to conclude, some of you know about this, I'm putting together a second edition of this report with Anwana Swami on the impact of control technology. And you can't read these, but I just mentioned what it is. So this is the intent of this is to highlight two things. One, success stories for control, and these success stories are really true operating real-world applications of control, not something that's been proven in the lab or in demonstration. And grand challenges for control research. So, what future impact on society and industry can be made in various areas? And so we are sort of still soliciting some submissions of what it would be more than we expect to have 78 or 80. The first edition had about 40 or so flyers. This new one would have about double that number. And these are just 2-page full-color flyers. You can't read these, I just mentioned them to you. This is a paper machine control, showing what control has done for paper machines. This is one from GE on locomotives and trains, trip optimization for railroads, for how contributed this one. This is ethylene plant-wide control and optimization. We're going to control and optimization on a plant-wide basis for ethylene plants. Benefits are $1 million plus per year annually, so very fast return on investment. This is Malcolm Smith's inerter, which was raced in Formula One and won his first race. This is control in mobile phones, Go Bernhardsen, there we have also contributions from Carl Ostrom, and this is just the success stories, and if any of you are interested in contributing or on challenges for control research, what are the challenges for the field in an application context, what will it do for society, what will, so we have, for example, we have one couple on cancer prediction, we have various other ones, sort of supply chain optimization, so we have about 20 some of things.
The deadline is when? What is the deadline?
Deadline is end of this year.
End of December.
And what we ask by way of submission, if you send me an email, I'll send you some examples. We just want a 2-page Word or PowerPoint document with some pictures and some text. And then we hired a production company. We hired an advertising company, actually, when we talk advertising companies, to create these sort of nice looking flyer classes or something from using the outside community. We've had some discussion, including with Bill, about who's really going to read this stuff. But actually, this is the most popular page on the IEEE CSS website, which is not saying too much, of course. But it says something. It says something, yeah. Okay, so thank you very much for your attention.
Thank you very much. We have 2 minutes for questions. Anybody have questions? Yeah, go ahead.
Can you please explain like the day-to-day of what you do at Honeywell?
Ooh, I'm hardly typical. So, I mean, there's so much going on at a company like Honeywell, it's hard to explain. So I day-to-day, every week from September through the middle of December, every week I'm traveling. Okay, so that's rare for an engineer. So, I don't know, would you mean a typical researcher? Is that what you think of?
Sure,
Typical person?
like a control
Like in your early years.
My early years, that's right, yes.
Before you became so famous.
Before I became the token industry person in the community, that's how I think of myself. Actually. So people work on projects, of course. Majority of the time spent. In our case, some companies do when we dedicated to one project. Most people in our case will be working on 2 or 3 projects at a time. These would be, some of these projects would be funded by the government, so it's all similar, although less far advanced, but similar to the sort of research work you might be doing here, government-funded research. Some of it will be funded by the business unit or by other internal resources, where the focus would be on some new product development or showing how some new technology is relevant to a business.
I guess my kind of question was more geared to like how specific or how much actual simulation do you do? In something like, let's say you were a control engineer who was designing some controller for or a piggy bank that would connect with the ECU, right? So that this turbocharger can actually work. What would you do every day?
The people who are doing this work I talked about,
Yeah.
they are on MATLAB and Simulink all the time.
Okay.
And
Not exactly
or
all right, think of it.
they're thinking of both. You're right. We have
They're on that, I haven't seen it.
It's not so contradictory, they're students. You know I'm right.
But they're developing new formulations and new algorithms, right? They're trying to understand the problems. They're talking to customers in many cases. That's because when I first joined the company, I never talked to customers unless we mean government agencies as customers. Now, at least in our company, we are talking much more to our customers, which from the R&D organization of a company, the customers are the businesses of the company, right? Or their customers. So in this case, it would be automotive manufacturers or engine manufacturers who are talking to them and understand what their requirements are and stuff like that. How can we solve this problem? How can we tweak this algorithm that we have, this MPC algorithm? How can we we develop this closed loop identification that way to things that are very powerful. But that would be our development was PhD level control engineers. Similarly, in other areas we work in, so in the process industry, similar advanced control for the process industries. In those cases, I think most people actually will often go out to the customer and go to a refinery and spend some time there and do some step tests or get the data. And then the research side, special government funded research is probably not that dissimilar to the sort that you do here.
especially when we do projects with industry. Very simple.
Does it help?
If you want to find more about it, you should try to get an industry person. That's how you're reaching all along. Then you will find out what they do. But anyway, before I ask you a couple of questions, I wanted to introduce Kubernetes Citizenship, who is here today. This is our benefit from the government shutdown. He is accidentally here stranded, so he's giving us a seminar in the afternoon in the mechanical engineering department. He's from Modelon. This is one of the companies that developed commercial products based on Modelica, and they were acquired by OnRamp Research.
No.
Not you, which is the one?
The other
Math
one.
Modelica.
We are independent, right? This
Sorry.
is the independent.
So they have actually, you have developed Log Modelica, right?
We developed Modelica,
It's
and
Java.
many libraries, Modelica libraries.
So if you want to hear this talk, he's going to come back to the roundtable at 4 o'clock, but he's giving a talk to the mechanical engineering conference room at 1:15.
Yes.
Yeah, so you can go there and, I know. I said there was a benefit from the government shutdown, but no benefit comes without cost, right? So, all right. So the question I have, and I'm glad you mentioned it, it's the same one I asked before, right? Because you had Smith's, inverter, right? That's a prime example.
Analog control, huh?
Exactly, because what was the problem? What is the analog of a capacitor in mechanical engineering, and why did he need it? Because of analog control implementation, and he used it for the suspension system of the Lotus car.
And if you try to do it digitally, it would just not.
Exactly, that's the point. So my wake-up call is, since I'm old enough to have such a wake-up, let's go back and look at the original days of controls. And actually, Carl Astrom is preaching that now for the last 3 years. Like you haven't seen any preacher preaching. We should go back and rethink about the physical implementation of controllers, right? In terms of, okay, you understand differential equation, you know what the performance is. In what physical structure is going to be implemented, right? And I claim that we don't have a good theory for that. Actually, it's a very weak theory.
But then you won't be able to access it on your iPhone. What is that?
Yeah, I think it's never going to be all of it, but I think
But-
some of the inner loops, so to say. I mean, the top level control is always going to be digital.
So, and one
But
of the things,
the inner loops with physical control.
that's why you see nice resurgence in modeling physics and so on and so forth. And actually, where do you see the resurgence? There are a lot of physicists now coming in and trying to understand control because they want to use what's called within physics design of feedback control, right? I mean, I learned it the hard way in '74 when I went to NYU, young person with a lot of mathematics, and I thought we were going to try to solve the problem of plasma containment, right? And there was a summer school at NYU in Korean District, and very quickly you realized that there was no way to have computer power fast enough to follow the dynamics of the system. So how the physics changes, they changed the geometry to create a cusp geometry, and then they were able to control it by within the physics, like the watt gallon. That's why I asked you, so what is your prediction in this direction in cars or automobiles or aircraft? And to answer his question, one of the major advances in 787 is that they actually changed the physics of the wing by going to composite structure, and that caused the change of the controller. That's the value of that work, I think, one of the most significant. So I want more examples of this type. Any
Well, I think
individual-
the airplane structure itself, like I'm sure there's some significant sense driven by controllability considerations, like we have rudders, for example, tails, right? In fact, one of the benefits I don't know if there or not that we maintain for advanced control in aircraft is it allows you to reduce the size of your tail.
Exactly.
So that's what.
So what if I change the fuel in the end? Do I have to redesign it, or your tool is going to be able to handle it? Suppose I go to a mixture of gas and gasoline or ethanol or something. What happens then? Because then all the chemistry is going to change. Do I have to redesign it, or what am I going to do? Yeah.
Actually, it's not entirely true that there's no theory. I think it is all the work of Jan Willems.
Yes, but it's, we have, but with the late Jan, we always have the debate, right? That it was not just behavior, it's also structure. And he was, to his credit, one of the few, he and Rocket and a few other people, that they actually paid their attention to behavior and structure, even in linear systems, right? Remember the theory about realizing controllers by RLC circuits and transformers and stuff like that, O'Brien Anderson and so on and so forth. But after around 75, right, more and more work was on dynamics and behavior, not so much on the behavior and the structure. Right? Where is the controller going to be implemented? And that's coming back now, I think, in a very big way. Primarily, in my view, from the emphasis on smaller systems where you can no longer separate sense, decide, actuate, and bring it back. It comes more into a mixed bag. And as Bert said, it's not going to be everywhere, but it's becoming an important component.
But I believe the natural theory of the behavior modeling of systems is applicable.
Yes, but you need a lot more.
Yeah.
You need the constraints of the platform and all that stuff. And you need to go beyond embedded systems, because embedded systems is particular kind of thing. Anyway, so what is the last question I have first? What's your advice to young people that want to go into controls or model-based system engineering, whatever? What should be the, and they want to work in industry, not academic. Since you come from industry. What should be your 1, 2, 3 do's or don'ts?
Control is many things to many different companies, so it's like hard to do. I mean, so messages from what I was talking about would be things like, appreciate the importance of knowing the industry and knowing the application. But, maybe that's not that, I don't think that's all the time important. And sometimes we hire people who we hire for their advanced applied mathematical skills, but they're relevant for, especially for government contracts. So I don't want to say that sort of competency either. But in most cases, I guess I would say that it's just very important to appreciate that this whole end-to-end perspective of, especially in the technology of control, which is hidden, right, and it's embedded somewhere deep into something.
Can I paraphrase? Are you saying that people have to be aware that they are not the only person who's going to work on the system, that they're going to interact with other people in different disciplines or systems and so on? That would agree with. What about the financial aspect of it? Is that important for them to have some appreciation of that?
Yeah, I mean, yes, so there's no other reason, frankly, there's no other reason for a company to be doing advanced control than within some horizon that varies from company to company. There is going to
No, I mean the cost of control, or the cost of design the kit. And of course the price, this is reflected, I guess. All right. You want to add something from your perspective?
From my perspective.
Sorry for the mistake. I always confuse you with what's the other company?
Mathematical, they were called MathCorp.
This was the one that bought by Wolfram Research.
Yes, they were both.
They developed now the system model.
Yes.
Experimental system model. We didn't take it yet.
What is very valuable from my part, so what we do is we work with model-based systems engineering and software tools around it, mostly. And what I find hard to find and find most valuable in employees that I look to hire is a combination of applied and theoretical skills. It's really the people that can bridge both sides well. I mean, my experience, for example, is that in mechanical engineering, the people know the application really well, and very often not enough math to be really useful. And it can be, on the other hand,
In electrical engineering is the reverse.
The other way around.
yes, and it can
Don't
be
be nice, just say.
it can be the inverse. What I really look for in hiring people is a good balance between understanding the industry and the math behind it. And it's very hard to find people that bridge both well. Somebody that can talk to the guy in the plant and still get the language right and understand what's going on there, and that can sit down and do the math. That's the people I really love to hire.
We agree. On that note, let's just remind again, we have, if you want to come, we can have a round table here, you're all welcome, 4 to 5. Let's thank the speaker again.